Dirac monopoles and Dirac strings.
Before I begin, I want you, the viewer, to abandon everything you know about physics, but not your sense of logic, of course. It is just a way to open your mind for what's to come.
Magnets are dipoles. The word dipole means it has two poles, so the term monopole would imply that it has one pole, but we know this should not exist. Paul Dirac, a 20th century physicist, says otherwise. Before that, note that an electric charge has a positive or a negative charge. Neutral charges aren't counted since they don't change anything. These charges have subatomic particles. A proton has a positive charge and an electron has a negative charge. We can do the same thing with magnets. Dirac monopoles, or more known as magnetic monopoles, are hypothetical particles that are basically just a particle that's a magnet or a quantized magnet. Magnets have a north pole and a south pole. We simply code the pole as the charge of a monopole. Then, we quantize it. To quantize means to make it smaller. Since we're looking for monopoles, we have to separate the poles. This means that a quantized magnet, a magnetic monopole, could have one of these two charges, a north charge or a south charge. So like an electric charge having a positive or a negative charge, the proton and the electron, a magnetic monopole has a north or a south charge, meaning a north monopole and a south monopole. Now that we have a concept of magnetic monopoles, how can we find one? Imagine a magnet. This magnet has a north pole and a south pole, yes? So we try to isolate both poles by cutting the magnet in half, but this produces two magnets that both have a north and a south pole. Now we take another magnet. We stretch the magnet to the point where it goes on infinitely. Since the poles are infinitely far away from each other, their magnetic field lines disconnect. They need to be close to attract each other and close their magnetic field lines. The end of the magnet has a south pole with nothing to connect to, as is the other end, the north pole. Hence, we have successfully obtained magnetic monopoles. But according to classical electrodynamics, Maxwell's second equation, Gauss's law, monopoles shouldn't exist. Since this doesn't work in the classical world, what about the quantum one? This could be backed up by Dirac's quantization condition, which says that magnetic monopoles exist if electric charge is quantized. Since we know that electric charge is quantized, the presence of the proton and the electron, it implies that magnetic monopoles should exist. To make our theory work, you have to think of a material where we stretch the length of a magnet to infinity so we can isolate the monopoles like what we did to a magnet earlier. A solenoid would do since we can regulate its magnetic field. Now, let's quantize this solenoid and scale it below elementary particles. We then stretch it infinitely so that lone magnetic charges are produced. This quantized solenoid is what we call the Dirac string. This string has a monopole to both ends. Oh, and here's another example. Bye!